Hello and welcome to The Explainer. Today we are tackling a really crucial, but sometimes overlooked step in any machine learning project, feature selection.
So let's just dive right in with a pretty powerful question. What if some of the data that you are meticulously collecting and feeding your model is actually making it worse? I know, it's a bit of a counterintuitive idea, right? We're always told more data is better. But today, we're going to challenge that assumption.
Here's the game plan. First, we'll talk about why just having more data isn't always the right answer. That's the feature overload problem. Then, we'll get into the solution, which is feature selection. We'll explore the three main strategies for doing it, and then dig into the really tricky part, searching for that perfect feature set. And finally, we'll wrap up by looking at why getting this right is an absolute game changer.
All right, so let's get into it. The feature overload problem. Well, it's a real headache in machine learning.
See, here's the thing. Just throwing every single piece of data you've got at a model can seriously backfire. You can end up with features that are totally irrelevant or maybe redundant, and all they do is add noise. That can confuse your classifier and actually drag down its accuracy. And that's not all. More features mean longer training times, it means data collection is more expensive, and you end up with these big, complex models that are just a pain to deploy and maintain.
So, now that we've seen the problem, what's the solution? Well, it's all about being selective. You can think of it like a coach who's picking the absolute best players for their team. You don't just put everyone on the field and hope it works out, right? You choose the best for each position.
So put simply, feature selection is this disciplined process of choosing only the most valuable and relevant features for whatever you're trying to do. It's a key part of what we call dimensionality reduction, and the goal is to end up with a smaller, much more potent set of features that really helps our model tell different classes apart. And this whole selection process isn't just for the raw data you start with. Nope, you can apply it to your primary input features and to any new derived features that you might have engineered along the way. The goal is always the same. Find that optimal set to work with.
Okay, so how do we, actually do this? Well, there are three main strategies for picking our feature dream team, and each one has its own philosophy.
So these three broad categories are filter, wrapper, and embedded methods. Each one really does tackle the problem from a completely unique angle.
This table really lays out the fundamental trade-offs. So let's use an analogy. Think of filter methods as a quick pre-screening. They're fast, they're cheap. It's like sorting job applicants by their resume before you even think about an interview. Wrapper methods, on the other hand, are the full, intensive interview process. They test how well a feature set performs with the actual model, which is super thorough, but man, it is time-consuming. And then you have embedded methods. They're like on-the-job training. The model learns which features are important as it's being built. It's a really great balance of performance and efficiency.
Okay, let's zoom in on those wrapper methods for a second because they highlight a massive challenge: the search for that perfect combination of features.
I mean, you really can't just try every single combination of features. As this formula shows, the number of possible subsets grows exponentially. If you have, say, 100 features and you want to pick the best 20, the number of combinations is just astronomical. A brute force search is simply completely off the table.
So, to get around this impossible search, we use heuristics. You can think of them as intelligent shortcuts. A classic example is sequential forward selection. You start with absolutely nothing, and then at each step, you add the one single feature that gives you the biggest immediate performance boost. It's a greedy approach, always chasing that biggest win right now.
But these simple, greedy searches have a huge drawback. It's often called the nesting effect. See, an early decision to add a feature can't be reversed. So a feature that looked amazing at the beginning might become totally redundant later on after other features get added, but it's stuck there. You can get locked into a path that's just not the best.
So if a simple one-path search can get you stuck, how do you find a solution that's more globally optimal? Well, this brings us to a much more advanced approach that's actually inspired by nature itself.
Genetic algorithms are a really fascinating way to tackle this search problem. Instead of just working with one feature set at a time, they manage an entire population of potential solutions. And then these solutions evolve over many, many generations, constantly improving to find the best possible answer.
And the way they work is brilliant because it really does mimic evolution. Each feature set is a chromosome, and its fitness is just how well it performs. The best chromosomes get to reproduce through crossover, combining their strengths to create potentially even better offspring. And to keep things from getting stale, mutation introduces random changes, which ensures we're always exploring new possibilities. It's this fantastic combination of exploiting what works and exploring new ideas that makes it so powerful for avoiding those traps we just talked about.
So we've covered the how, but let's refocus on the why. The payoff for doing all this work goes way beyond just a small bump in accuracy.
So why should you really care about this? Because effective feature selection leads directly to models that are cheaper to build, faster to train, and way simpler to understand and maintain. And maybe most crucially, by removing all that noise and focusing on the most important signals, it helps your model generalize better to new, unseen data, which, let's be honest, is the ultimate goal of machine learning.
But maybe the most important benefit in today's world is how much this contributes to explainable AI. I mean, if you're building a model for something critical like medical diagnoses or financial decisions, you just can't have a black box. Feature selection helps you understand which inputs are driving the model's decisions, and that makes your AI so much more transparent and trustworthy.
Ultimately, feature selection is both an art and a science of helping your model focus on what truly matters. It's about making sure it's learning the real, underlying patterns, the signal, instead of just memorizing the random quirks in your training data, the noise. Which leaves us with one final question for you to think about.